better morning than I am. You could scarcely have a worse one. All right. What am I talking about? Yes, right. Okay. Oh. Okay. Okay. What did we talk about last class? Anyone remember? I sure don't. What about them? Look at some examples of graphs, right? Talk about the problem of cycles. You need to worry about cycles and things breaking if you don't keep track of things, etc. Okay, so today I want to start with our first graph algorithms. Again, some of this will be a little familiar to you from school. That could be dangerous because you have been taught maybe in a certain way, and that might turn out to be not exactly the way we're going to do things here. So, especially if you've had CS before and seen some of the stuff before, you should pay especially close attention. So what I'm going to do is start with a simple task, like maybe the simplest possible thing you can imagine with a graph. Okay, so we've got this graph, got a directed graph. Right? And what we want to know, so every node is going to have some kind of content, right? Basically, it's payload. The thing we used to call the value in a tree, we're going to call the content when it comes to a graph node. And it could be any rich content, right? We're not going to judge. It doesn't have to be a string. It could be any complicated thing at all, right? It may be a whole bunch of metadata about, for example, if it's a graph of cities, it might be a whole bunch of data about the cities, about its its population and its name and its demographic information and all of its neighborhoods and so on, right? So can you think of other graphs where the content of a node might be complicated? Talk to your neighbors and come back with at least one example. Go. Go, go, go. Morning. Dude, content of the node of a graph is the question. Okay, 5, 4, 3, 2, 1. We're back. How about we start in the back? Content of the node.
Could be another graph, possibly.
Could be another graph, but I want a concrete example. So it's true, it could be, but let's come up with a concrete situation and what the content might be. Next group.
So the node is a person, and you have all the bio data.
What kind of graph might have that?
Friend network.
A social network, right? In fact, the whole point of the social network is to hoover up as much information as it can about you, right? To sell to like enemy governments or something like that. Yeah, he didn't say that. No, it's, yeah. Okay, so so it might be, so in Facebook, for example, right, they're trying to accumulate a whole bunch of information about you, not just the information that you provide, but also information that they can infer. So in fact, the content keeps growing over time, right? Now they've discovered you're a fan of football. Now they've discovered you're a fan of, opera, whatever, and they keep adding more and more information about you, right? So in fact, the content could be extremely rich information, might even be a graph itself. It might have some interconnections between those things, right? It might be a sense of the strength of how much you care about a pair of things, right? All of these things could be there. So we're not going to make judgments about content. And in fact, in the homework you're going to do, you'll actually multiple homeworks, and you'll have fairly rich content in one of them. The other one's going to be somewhat more agnostic to the content. Okay? All right. So we've got content, and so critically, when we have an interface, we have nodes. Nodes have content, and for each node, we have a list of other nodes that you can get to. Right? As we talked last class, we're going to use this level of indirection, okay? Common term that you'll end up seeing in computer science is level of indirection. Meaning, when you ask for the list of neighbors of a node, you're not going to get the nodes themselves. You're going to get a key for the node, a way of looking up the node in the graph data structure. Right? Do you remember we did 2 different kinds of keys last class? 2 kinds of keys. What were the 2 kinds of keys we did last class? 2 kinds of keys. Anyone remember 2 kinds of keys? 2 kinds of keys? Anyone? 2 kinds of keys. 2 kinds of keys, yeah. String. Number. So we said we have indexed graphs where it's the position in some list, that's the key, right? Or we have some sort of name value association, like a key value pair kind of thing, right? And then it's the name that you look up, right? Either way, there's some lookup process that occurs to get from the name to the actual node itself, okay? So we're going to assume, so that's what you call a level of indirection. You didn't get to the node, you got to a thing that gets you to the node, right? Do you recall why we went through the level of indirection? Here's an exercise. Let's say we don't want to do that, okay? So I'm going to draw you a simple graph, okay? Let's just say, here, let's take the simplest possible graph. So I'll just use the example we talked about last class. So the content of this node is it's Newark Airport. Content of this node is Providence Airport, okay? So the content is EWR and PVD, okay? So, what is the list of neighbors of this node? I'm hearing different answers. So, some people said PVD. Everyone okay with that? No. What is the list of neighbors? If it's not PVD, what is it?
The node.
The node whose content is PVD. It's a subtle difference. Okay? The true neighbor is the node whose content is PVD, and its neighbor is?
The node whose content.
Say it all. Everyone say it. I want everyone to say it. The node whose content is EWR. Okay, good. So, node, okay, there's only one kind of node, okay? It has some content, and I'm not even going to bother what the type of the content for now. What I care about is list of neighbors, which is what? List of node, right? Not a list of a key, it's a list of nodes itself. Okay? So, sit down, so talk to your neighbors and generate for me the data structure for this pair here. Okay? So represent this graph using this data type. Go.
Because otherwise we're just that's probably why he's doing he doesn't also so like new nodes
5, 4, 3, 2, 1. We're back. Somebody have some code for me? Good.
So we call the one like node 1
So node 1, let's call N1, okay?
equals node
Uh-huh.
of EWR and,
EWR,
and then comma
Uh-huh.
list of N2
list of N2, okay?
and then N2
Uh-huh.
equals node
Uh-huh.
of PVD and then a list of N1.
Good. Good. Great. Everyone okay with this?
no.
No? Why not?
These N2s are defined yet?
When you write N1, N2 is not defined. That's fine, right? We just move this line of code up here. Okay? So, that's our problem. Okay? We can't define one without defining the other. I mean, you could take an even simpler case, right? What if I just had this node go to itself, right? So I would write something like N is node of, they say in this case EWR, right? List of N, right? That's going to produce an error, but we saw a way around that error, right? We write rec. Does that solve the problem? Solves the problem, yes or no? Yes. No? Why not? It no longer gives me an unbound ID error. What does it give?
Just keeps going.
It keeps going.
There was something else.
Dim birds. It could keep going. It could also throw an error, right?
There's no PVD.
It doesn't.
Well, no, this
Well,
is
I'm
right.
talking about the amended graph where it just has that cycle. Sorry. Yeah. Anyone remember? Did you get an error? Did you get an error?
It sets n to some like weird default value that.
It
doesn't
said
really
that
matter.
it's been defined but not initialized. Yeah, that thing, right? Okay. So the point is, no matter what it does, it's not going to work, right? It's not going to work in either circumstance. It's just not going to work, right? So there is actually, by the way, a way in Racket and Pirate to actually write these things. That's pretty esoteric and it's very language specific, so I'm not going to get into that in this course. So I used to teach it that way and I decided to stop teaching it that way. So that's why we can't write it this way, right? Instead, what we can write is we write a key over here, right? Write a key over here, and the key is later on defined, right? That's the level of indirection where the graph structure lets us look up the key later, and that's what lets it be defined. Okay? It's a bit subtle. Like, it's a little bit like, well, you know, it's two functions that refer to each other have the same issue, right? One function's going to call the other, second function's going to call the first. How does it work? Well, it actually works by doing this kind of thing automatically for you. This is what the compiler does for you, so you don't have to do it. Yeah?
Is there a way to deal with two nodes that have the same content in this framework?
Yeah, so because we have not made any judgment about, actually, you know what? Hold that question for a few minutes because it's going to be very relevant to what I'm going to do next, okay? Is that good? Yeah. Okay, so now do you see why we need keyed nodes, right? We need some notion of a key so we can eventually look things up and everything is well defined and we don't have this pain of constructing it in the first place. Otherwise, we can't even construct it, okay? Or we could do it with some like special language construct, but we've decided to stop doing that in this course because it's too specific to the language, right? This is a general strategy that you can take to other programming languages. Okay? Another way to think about this is I mentioned in class that you can think of this this index node as a matrix, right? So what's going on here is we might have a matrix that's PVD, EWR, PVD, EWR, right? So we're going to basically put a 1 here if there's we need a convention, right? If there's an edge from here to here, we put a 1, right? So we put a 1 over here. Would we? No, we don't. We put a 1 over here. We put a 1 over here. We put a 0 over here. In the modified version of the graph, where if I had just this, right? What changes? So talk to your neighbors and tell me what the adjacency matrix looks like. I want you to tell me in this order, so like 0, 1, 1, 0, right? So talk to your neighbors and tell me what the new adjacency matrix should be in that order. Okay, answers? Doop, 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 doop. Yeah. 0001. Any other answers? We're good? Is that right? Yeah, good. Okay, very good. Okay? So, you pick a convention, you create a square matrix, you pick a convention about which is the source and which is the sink base layer. Where does it start, where does it end, right? And then you just put zeros and ones and that's another representation. That's effectively kind of what you're doing with the list representation using numbers. Right? You just, instead of writing it as a matrix, you're writing it as a list of lists, essentially. Right? The problem with this representation is you need some other place to hang the payload off, right? Like the content has to go somewhere. So what we're doing with the indexed representation is basically tracking the payload as well. Does that make sense? Okay, good. All right. Okay, so now that we've agreed on the representation, let's start building some code. The simplest possible thing you can ask about for a graph is a node there? Is it there or not? Okay. Well, that's kind of not too hard to do, right? How would you check whether a node is in the graph? Yeah.
Just go through every single node.
Go through a list of nodes and just check whether then that's the node or not, right? So more interesting basic question is, given two nodes, given a starting point to start from, can I get to the other node? right? And this is a obvious question you want to ask in several graphs. Starting from this city, can I take a sequence of flights that gets me to that city? And airline search engines have to solve this all the time, right? Sometimes you will ask for a certain thing and they'll say, sorry, there exists no route, right? And it may be that what they mean is there's no route on one airline, maybe there's on a different airline, but there exists no route, right? Actually, it's a little trickier with the case of airlines because it's pretty hard to get an airline search engine to give you a route that is 17 flights long, right? There's actually a reason for that, and it has nothing to do with graph theory. So, so I won't go into details of airline routing here. But so they typically mean is there a route within about 3 hops or so. Okay, but setting that aside, the question is there a route? This is the same thing that you deal with on social media, right? Can I get from this person to that person? And in some sense, that's the whole business in some ways of LinkedIn, right? LinkedIn tells you this person is available to you within 1 connection or 2 connections or something like that. What they're basically doing is computing those routes, right? So is there a way to get from here to there? There's a general question that you can ask of lots of different kinds of graphs. Maybe not every kind of graph. It may not be interesting in every kind of graph, but it's generally interesting in most kinds of graphs. Okay? And then we're going to refine that question as we go along. So that's the question we want to ask. Okay? Can I reach? So it's the problem of reachability. So I want to reach, given some graph G. Okay? And what I want to know is, can I get from N1 to N2? Now, there's a little bit of a question of what it means to be N1, right? Do I mean, like, could I have a graph where I have the same content, so back to that question, I have the same content in multiple nodes. So I want to know whether this is even a realistic problem to think about, okay? So what I would like you to do, talk to your neighbors, and what I want you to come back with is either no, which is fine, hopefully you've spent some time thinking about it before coming back and saying no, or if you say yes, give me a concrete example of a kind of graph, and for that graph, how could you possibly have 2 different nodes that have the same information? Okay? Just the content part. Go.
There's this thing
Five, 4, 3, 2, 1. We're back. How many for yeses? How many no's? Wow. Okay. Well, the no's have it easy because they don't have to provide any evidence, right? It's like, nope. Okay. So yeses. Anyone want to give me a yes? How about we start back there? Let's go from there. Are you a yeses or no's? You're yes. Okay, great. Give me a concrete example.
We just said that like if 2 people have the exact same name.
So in a social network, 2 people could have the exact same name. Not that that would ever happen in practice. Okay. So if all your information is just the name, then yeah, actually there's a very high likelihood of having clashes, right? Next, yeses or nos? Yeah, yes?
No.
Your nos. Okay, well, what do you think about that example?
What about like the adjacent like nodes?
Ah, we just the content.
Oh,
Just the content. Here's an interesting question. Could you have 2 different... So let's just take the social network, okay? So this is a really good clarification because, so I asked the question in terms of content, right? Like then it's just if all they have is a name, then of course the 2 different people could have the same name. But you're pointing out maybe it's more subtle than that, right? If we talk about nodes being equal and we're considering also the list of adjacencies, then it would be really weird if two different people with the exact same name had the exact same set of friends, right?
But it's not impossible, though.
It's not impossible, so maybe you should consider that possibility, like if you're a careful programmer, which you don't have to be once you leave 19, but in 19 I have some expectations. We have standards around here, people, okay? But think harder. Is it, like, how unlikely is it that that might happen? That's really the question, right? Maybe if it's so unlikely, maybe you really don't need to consider it. How unlikely is it that you might have two people with the same name and the exact same list of friends, like two different people supposedly? Yeah.
Probably not that unlikely, because two people who just create accounts have no connections, and they could have the same name.
Ah, ooh, pretty nice. Two brand new accounts, right? Base cases are always important. Base cases are empty lists. Two different people who just create accounts, have no friends, okay? But that's going to change after some time. Good try, good try. Yeah.
Or if the same person makes it twice.
Same person makes it twice, okay? Which you're not supposed to do according to the terms of service. That person, okay, don't report. Yeah, door's not closed. Okay, good point. So somebody makes it twice, that would certainly be a cause for that. Yeah?
Oh, I was just saying for the reason for like now, but
It's 2018. We need to think about attacks. Impersonation attacks. If I were trying to impersonate you, I'm not going to pick a different name, I'm going to pick the exact same name, and I am going to make sure I get all of your friends as my friends. Okay? This is by the way, an actual attack, an actual kind of attack that has happened on social media. Essentially what I would do is I would create a new account, I'd use your photograph as my photograph, use your name as my name, friend all of your friends. Your friends are going to be like, okay, obviously he's, they don't even remember whether you have an account or not, especially if you don't post very often. And, they're going to just friend you back. And pretty soon you're going to have reproduced the friend network. Now, once you have that, you basically control that person's identity online. Right? So you can use that identity, for instance, to basically request money or something like that. Now you might think, well, why would anybody do that? I had a long conversation once with a flight attendant on United, and the flight attendant said, well, I never like to use social media. I said, well, you of all people really should, because here's the attack, right? I'm going to create an account in your name. I can actually see your name right now, so it's not very hard. I'm going to create an account, okay? Now, the thing about finding friends is actually a little tricky. How do you figure out friends? Well, it turns out one of the things you can do is you can find somebody's friends on one social medium and go take it to the other social medium, right? So you look for friends on LinkedIn, and then you find the corresponding accounts on Facebook, and then you try to find their friends on Facebook. You can automate a chunk of this attack. Right? People have actually automated chunks of this attack. So now I'm going to create this person's account on the other social medium, say Instagram. There's always a new one, right? So with enough people, so you create, well, Google Plus. Much bereaved Google Plus, but anyway. And then, well, you're a flight attendant. So you're the perfect person for, so-called 419 scam, right? I'm stuck. I took my flight. I went to such and such place. I'm now in Azerbaijan, and our planes are stuck, and I need to pay my hotel bill. Somebody wire me some money, right? You are the perfect candidate for this kind of attack. And that's why you need to control your social media presence to prevent impersonation attacks. And I clearly, it was like the worst teaching moment of my entire human existence, because a flight attendant heard me say all this and said, and that's why I don't want to stay off social media. I'm like, oh! Epic fail. Okay, but that's why you should. So, if you've learned one thing this semester, keep in mind that there are impersonation attacks. So an impersonator, by definition, is trying to construct exactly the same note. Okay? All right, so we have to think about what it means to go from one node to the other, and what are we really searching for? Are we searching for a node? Are we searching for a particular payload? And there are different kinds of reachability that you would get, right? You might simply want to know, starting from this node, can I get to anything with just a particular kind of content, right? So if I have a graph of T, then all I want to know is, can I get to that kind of content, or do I get to that kind of node, right? What that's going to do is, in effect, it's going to have slightly different equality predicates, right? That's what we're going to do. We're going to have slightly different equality predicates. You could even just get rid of this entire mess by simply saying found. I can't put question marks in silly language, sorry. And that's going to be a node to Boolean. Right? And you simply say, where am I starting from, and how do I know whether I'm done? Right? And this can take the node and it can skip the node's identity, it can use the node's identity, use the key, not use the key, use the content, not use the content, do whatever it wants, look at the adjacency, whatever it wants, right? That would be a good way to generalize this function and skip over the entire, so this is the way you will not see it taught in traditional textbooks, okay? But this is really the right way to think about it. Right? Instead of passing 17 more parameters, do I send the node, do I send an equality predicate, do I send several other things? I can just send this in and then automatically deal with the whole problem inside that function. Right? And now you get a general, this thing has the expertise on traversal, this thing has the specialization of that expertise for your particular need. That is a separation of concerns. That's how you build good software. Okay? Question?
Yeah. So just in terms of like node structure itself, why is the tag not separate from the content? It seems kind of silly to like have to compare giant like content streams next to each other. Like
The tag, do you mean the key?
or yeah, the key. Sorry.
Well, the key, in this particular case, I was purposely writing the non-keyed kind of node, okay? So the non-keyed kind of node, so to demonstrate that we can't do it, okay? So what I really need is also a key, right? And then that becomes a list of key. That's the kind we're actually going to use this semester, and I wanted to demonstrate why we need it. Because I sort of alluded to it last class, but I didn't really demonstrate it, okay? Now, does that make you happier? Good, yeah.
And during the semester, are we going to end up with nodes that can have two of the same key or no?
No. That is the one rule. You cannot have two things of the same key. Okay? The
Yeah.
content, so the point is, thank you for asking. The thing is, those two people, so my impersonator and I on Facebook, we may look identical to the outside world, but internally inside Facebook, we're actually two different accounts. Okay? So think of it as a count, if you will, right? That's the key. Every system of data indexing ends up having something called a key, which is a truly unique thing. There cannot be any duplicates. It cannot be forged, right? External entities cannot forge it. So the same way on Facebook, I mean, I can steal somebody's password, but that's not the same as forging their account. That's a subtle difference, right? The account has its own integrity. The password may not have sufficient integrity, and somebody may be able to guess it or steal it or something else. But in the process of using the password, they go back to the same account that they went to before. Right? Does that make sense? The account has an identity of its own, and that account is truly distinct from all accounts. It may be that all of its content looks identical to some other account. Right? In fact, you could imagine an algorithm that basically walks your graph and asks, are there duplicates? Right? Is there impersonation going on? Now, of course, impersonators never get it exactly right, so you have to be careful about how you define the question. But you can certainly imagine one that walks the entire graph, right, which is a collection of nodes, and asks, are there two nodes that are obviously distinct, but yet their content and the list of keys is identical? Right? That would be a basic impersonation test. Make sense? Yes?
I'm just a little bit confused. What does the found function do?
So I'm going to walk the graph, right? And I want to know whether I can get to blank from a starting point. What does it mean to get to something? Well, different uses are going to have different notions of what it means to get to something, right? Some uses are going to say, can I get to something with a particular key? Some other uses are going to say, can I get to something with a particular content, right? So one of them, so in the case of, say, airports, for example, I want to know whether I can get to the airport with the key PVD, okay? In another case, I might want to say, can I get to something, can I get to a person who is, 5 feet 10 inches tall, right? And I don't care which person it is, I just want to know if I can get to somebody of that height, because I need them to come and, lift something, take something off a shelf or something like that, right? So what this, yeah, that was a really great example. Okay, so that's how that's how I get things off shelves. I post to social media and like deal with stuff. Okay, so the point is, I'm going to give this predicate. This is like filter, right? Remember what we did with filter? We give the information to the predicate and say, you decide. I don't want to have to be the one who makes that choice. So the same way, we're going to give the node, as we traverse, we're going to give each node to found, and found is going to tell us, for this particular application, am I done or am I not done? So analogous to filter. Yeah.
But then, like, wouldn't you need to somehow put in the node that you're at too, in order to make this, like, because if not, how are you going to know, like, how's found going to be able to compute?
Because it's going to be, how did the predicate and filter work?
Because you had to pass it to your list.
Yeah, and you're giving it a graph.
But you're not inputting a graph into found, you're only inputting into...
Because at each point in the traversal, it's going to give the current node that it's looking at to that predicate and say, is this the node? Filter's predicate doesn't get the whole list, it just gets an element and says, is this the element? This predicate is going to get an element and be told, is this the one, is this the kind of thing you're looking for? Yes, then I'm done, otherwise I need to continue. Okay? Think about that for a little bit. It takes a little while to settle in. Okay, good. Any other questions? All right, so now, right reach. Question before you start, hold on. Any questions? Sorry?
What's the structure of
Graph is a list of nodes. Yeah. Yeah.
Do we also need to write found?
No, found is being given to you as an argument, right? It's the third argument to reach. It's the predicate you're going to apply given you visit a particular node.
You're asking, which is the same question. You want to ask if I can use it, what do I do? That's my question. You know, I just...
It depends on the situation. It's not efficient.
Then you take the first one, you say,
Well, but it has to be started instead of node.
No, but we don't.
something, so like each time you're gonna have to do like reach, you're gonna have to apply that to each
You got all the adjacencies. We don't have node is only a single I mean, when I say go back, I mean like we want how do you pass? We want to full
The graph has nodes that are not
No, you want to follow the entire list, and then like
For example, on the board,
running reach on that, ending it, lowering it so you see, when we close it, we want to check, it's not just for the first one, we want to reach the whole list for some and you want to reach the boundary all the other ones. you get to one, it has to keep, and you have to go get there. And you have to go back.
Five, 4, 3, 2, 1. We're back. What is the central problem you're going to run into? Central problem you're going to run into. Central problem. New people, new hands, new hands, new hands, new hands. Yes.
You don't want to get stuck in a cycle continuously.
Have you seen this problem before? Have you seen this exact same problem before? No, because we haven't had cycles before. But have you seen a similar problem before? Why does this sound a bit familiar? We need to make sure that we don't traverse, count something we've already traversed / counted. Remember? Yeah, that one, right? So with DAGs, we had that problem. We had to keep track of all the things we've already visited because otherwise we end up double counting. Here it's much worse. If we don't keep track of the things we've already visited, we might very well keep visiting them over and over again. And while our airline might appreciate the revenue, we would be pretty unhappy, right? Furthermore, imagine that I asked you to tell me whether something is reachable. That's truly not reachable. I say, starting from here, can I get to this node? There is no way of getting to this node. So you better make sure you've kept track of all of the nodes that are reachable. And at some point, you're going to be, I can't seem to get to any new nodes, and I haven't gotten to the node that you wanted me to. Therefore, it must be the case that the node is not reachable. For that, again, you need to keep track of the history of all the things you've seen. Okay? Do you remember the twist we ran into, keeping track of the history of all the things we've seen? We don't only consume the list of things we've seen, we have to return the list of things we've seen, right? Because that's how we convey information from different sites. Okay? Same pattern, exact same pattern every time. So that's why I did DAGs, by the way, because it's much easier to see the problem in the setting of DAGs, gets you warmed up to the issue, and then the same problem carries over, but in an even more extreme case for graphs. Because now it's not just a matter of getting the counts wrong, it's truly a matter of going into infinite loops if you don't do it right. Okay? Same pattern, you're going to have to do the same thing. Okay? So the same way, if you came down over here, you come down over here, you have to remember that you've already seen that, otherwise you're going to do that all over again, and so on. Okay? Good. So I'm going to let you think about this a little more, and then go off and read the code in, and we've already done this code in class. But also, you're going to have to write this for your homework. Okay? You'll run into this problem when you solve the homework, and you'll get it right? Because you'll write really great tests, and then your really great tests will prevent you from getting into bad situations, and it'll be awesome. Right? Good. Now, I want to talk about something really important about graphs. When we talk, and as you know, in this course we care about the big O complexity, the time complexity specifically, of our computations. So I want to talk for a moment about what it means to be big O of a graph algorithm. Okay? So let's take our simplest graph algorithm, which is reachability. Okay? So reachability, well, is it going to have to visit every node in the graph? Maybe. Yeah, maybe, right? It's a little subtle because if the graph is disconnected, right, then it's not going to actually visit all the nodes. But in the worst case, it's actually going to visit all the nodes, right? We're doing worst case complexity, so worst case it's going to visit all the nodes. Okay. So how much work does it do at each node? What's it going to do? What is reach going to do when it gets to a particular node? It's going to call found, right? So we don't know what found is going to do, but from reach's point of view, it's only just going to visit the node and get back a Boolean decision, right? So ignoring the complexity of found, assuming found is a constant time operation, like we're not going to charge reach for different founds that you wrote, right? You wrote some very complicated found, that's not reach's fault, right? From reach's point of view, basically there's an atomic cost to calling found, and then whatever the cost of found is a separate matter. It's a multiplicative factor, right? So reach is going to call found on a node, and make a decision based on that, right? If the answer comes back as true, it's done. Otherwise, it's going to continue traversing, right? And so essentially, reach, and what's it going to traverse? Is it going to traverse some of the edges? Obviously not. It's got to traverse all of the edges. Otherwise, it might miss the edge that was going to contain the thing that we were looking for, right? So it needs to traverse all of the edges at least once. It needs to visit all of the nodes, worst case, at least once. But the whole point is it's remembering the nodes that it's visited, so it doesn't need to revisit them again. It better not, right? Because that's where the infinite loop comes from. So it's not going to visit a node more than once. And since the edges are attached to the nodes, if it's only visited a node once and visited all of its edges, it's never going to visit the edges a second time. Okay? So it's going to visit all of the nodes once, all of the edges once, in the worst case. Right? Make sense? So this sounds like what? This sounds like a linear time algorithm, right? A canonical linear time algorithm. And my sounds like may make you think like, okay, what's he hiding? Okay? I'm not hiding anything. It is a linear time algorithm. The tricky thing is, what does linear mean? Right? So when we talk about graphs, we have vertices and we have edges, or nodes and edges. Right? Let's say we have k vertices. Okay? How many edges does the graph have if it has k vertices? Talk to your neighbors, come back to me with an answer. Go.
In the worst case, like everything because for each node, that makes sense. I remember doing this at
Five, 4, 3, 2, 1. We're back. Okay, so what do we have? What is the least number of edges we could have? Zero. Everyone sees that, right? Completely disconnected graph, right? It's a statement of our modern times or something like that on a social network, right? So nobody's talking to anybody else. Okay, what is the other extreme? How bad can it be? Well, let's take a look at this graph over here, right? How many edges could this this vertex have going out? 4, right? So I have 1, 2, 3, 4. Any more? Yeah. Aha, very good. Thank you. 5. Okay. More? Where?
Multiple edges of one.
No, we're assuming we have only one. Okay. Good. Okay. Now, how many edges can this have?
5.
Okay. You see that, right? So 1, 2, 3, 4, and 5. Right? And 5 and 5 and 5 and 5 and 5. So basically, every vertex can have an edge to every other vertex, right? So the worst case is we could end up with k squared edges. Okay? And given this number of vertices, any of these range is possible. A priori, for the fact, there's no way to know. Now, in a particular domain, you might be able to say, I have a domain that has the following characteristic. But in general, there's just no way to know. Any of these things is possible. Okay? So when we compute the complexity for graphs, well, if we compute the complexity in terms of number of vertices, well, we're visiting all of the edges too, right? Like in reach, well, not always, but in reachability, we're visiting all of the edges. So, which one are we actually linear in? We're linear in the number of edges because we have to visit the number of edges. That means we're actually kind of quadratic in the number of vertices, right? But is it the case that we're always going to have a quadratic number of edges in relative to the number of vertices? In fact, it's relatively uncommon. People have done these kinds of studies, and it turns out that, like, you know, things are generally linear-ish and maybe super linear, but generally far short of quadratic. Okay? And in different domains, people have done studies about this sort of thing, right? So really what we need to do when we talk about the complexity of a graph is it's really a function of two things, okay? It's the number of nodes and the number of edges. Right? There's always two parameters, how many nodes, how many edges, because this could be vastly smaller, this could also be vastly larger. So in our case, what is the complexity? When we say linear, what do we really mean? Is it E? Does that mean E?
No.
Is the answer E?
No.
Why not?
Not always.
It is E.
If there's no edges at all,
It just stops.
it just stops, but are we actually going to visit at least one node?
Yes.
Yeah, so it's at least slightly bigger than that, right, within a constant, you're right, okay? But, so really, what's a good way to think about the complexity over here?
Max.
Yeah, you can think of it as the max of N and E, right?
Wait.
Max? Min?
Some.
Sum?
Not for this.
Quotient? Yeah, why not? Let's divide. Okay, I'm going to let you think about this. I'm going to let you think about this because this is the stuff you're going to have to confront as we start doing graph algorithms. Okay? Okay, good. Go think about this, debate. We'll talk about next class. We'll start doing more graph algorithms.